So last time we talked about numerical analysis. This is the second episode that is related. So I mean a little bit, but we will do something very different. You don't need to be there. That's why I understand. So numerical analysis of SDE. And for this, we will talk about first the art case. Then there is the medical case. Turns out that the art case is already hard. So the second one will be even harder. All along, I will ask some open questions so that you know how much work there is left to do and how little we know, because it's actually very hard and nothing is done for the moment. So maybe just let me recap what we did last time. So we studied in particular a set of equations, f of x t, but here we'll focus on additive noise. This is just a constant, sigma greater than 0. F is a vector field that is typically infinity, Lipschitz, and under these conditions, there is a unique solution to this SDE. And we said there are different ways to approximate the solution. The first one is the strong approximation, which means approximating x of t. Approximate x of t given w of t. So we know w, who is a very irregular function. It's just almost alpha Eulerian, if that's all. And we try to approximate x of t. We said it's very hard. We presented the Euler method, and I said that we will not look at this one because that's not what I want to do. Then we have the weak approximation, that is approximate the load of x of t. So we don't need w, we just need the load of w that we already know. And what we want to approximate is this, it's u of x is equal to expectation of the test function of the solution, knowing that we begin at x. So we start at x and we want to approximate the average of the function of the solution. We saw that if phi is the identity, this is the expectation. If phi is x squared, this is the variance of x. And basically, you can show that if you get all the moments, the polynomials of x, in expectation, you have access to the law of x. This is some basic probability theory that we won't talk about. But the idea is that for this kind of dynamics, this appears in molecular dynamics. If you take phi to be x squared, I simplified, what you approximate is the temperature of the gas. So that's actually exactly the quantity that we're interested in here. And finally, we saw it very fast, the approximation to the inbound measure that we won't focus on today. We'll just focus on this one today. It means that if t goes to infinity, your physical your gas will reach an equilibrium. It will reach a temperature at equilibrium, and you just want to approximate the temperature at equilibrium. So you have a last approximation that is when t goes to infinity, and you have some weaker conditions. So if you have a strong scheme, it's also weak. If you have a weak scheme, it's also of the same order as in motivation. Okay. So just to fix the notation, we take t in 0 t. We fix a step size. We decompose with x to t 0, and then we have h to h n minus 1 to h, and this is equal to n h. And so we want to approximate x of tn, which is equal to nh, and we approximate it by Xn, well, this is the numerical solution. All right, so we have a scheme that approximates x of t. And what we defined last time is a local order of that a numerical scheme has local weak order t in Xn if for all n there exists c such that expectation of phi of x h expectation of phi 1 is less than c h. This is exactly the same definition as for the deterministic ODEs, except that we have phi is equal to identity for ODEs. There's no need for expectation because it's not random, but the rest is the same. So note again that here we approximate these quantities. It's the same as this one. I just forget about the initial condition. So what we want to approximate is this quantity, and we approximate it after one step. So last time we did a complicated proof, but quite a funny one, to show that if you have local, we call the P, and you're stable, then you have global, we call the P. So we don't need that, we'll just study the local order P today. As I said last time, there are different kinds of error. You have the Monte Carlo error and the discretization error. We'll just focus on this one. Okay. Is it okay?
Is that an H?
Yeah, H is a step size. It's a time step. And the question here is how do you create integrated? And the answer is the same as for ODE by using Taylor expansions. Right. So we will do Taylor expansion of this first, and then Taylor expansion of that somehow. And we'll compare the two of them. And if they match up to a certain order, P, then we will have order P. Right? So let's do it. How do we make a Taylor expansion of this? We've seen it now. We'll redo it, but this is exactly what John Mark presented, what I told about last time with the generator. We look at the exact solution. And I write u of x t, again, is the equation of a polynomial, think of it as a polynomial, of x of t, knowing x0 is 1. And we've seen the forward not feasible, the backward Kolmogorov equation. Which says that d for the dt is equal to n. The generator of this. Do you remember that we've seen that a while ago? Right? Somehow, maybe we've seen that. So actually, this quantity satisfies a PDE in high dimensions. There's nothing stochastic here. And L is given by this. So L phi is equal to 5 times F plus 0 to 2 dimension phi. And F and sigma come from the equation. So you see that basically the generator links exactly the quantities that appear here. This part gives the first order term, and this one gives the second order term. All right? Yeah.
Prime is in time and the velocity is in space.
Sorry?
Prime is in time and the velocity is in space.
No, when I write prime, it's always in space, there's no time. Here is L for your right. L phi of x is phi prime of x f x. Function phi of x. And what I mean by this is the sum of d phi over x I f I. Well, it's actually important that you mention this because we'll work with way more complicated things like this. But anyway, I have this kind of heat equation. It reminds us of the heat equation if x equal to 0, right? So then you agree that u of x h is approximately equal to u of x 0 plus h u of x 0 plus h2 over 2 t blah blah blah. Yes, it's Taylor. Now I can just replace by this. So I have u of x h is equal to u of x 0. So this we know is phi of x. Yeah, just if you put t equals 0 in this, it's phi of x 0, which is x, phi of x. Plus we replace this term by lu at time 0. So it's just phi. And then we move on. So it's just because the solution of this equation is exponential n, exponential tn times phi. So that's why we obtain the series of exponential tn. Right? Yeah.
Equality here, almost sure, or is it stronger, weaker?
It's from now on, I'm doing numerical analysis, which means that everything is done with the hands. And I assure you that there's a way that everything can make sense, but I just don't want it. Yeah. So you're right. I will write something like that. But I mean, it's the intuition that counts. So this is very important. This is extremely important. Should I even keep it here and write 5 guys? It means that this quantity here. So as I said, we want to compare this quantity with this one. We started with this one. This one satisfies the Taylor expansion, which is given by this. Well, L is this function. And now, well, we would like for we know this term, What is this one? Let's compute it, right? So L2 phi is equal to L applied to L phi. So it's phi prime f plus sigma 2 over 2 delta phi from that plus sigma 2 over 2 Laplacian of phi prime f plus sigma 2 over 2 delta phi. Nice. Well, let's do it. I will just write the results so I can find it again. So what you have is phi section f plus phi prime f prime f plus sigma 2 over 2 phi f plus sigma 2 over 2 Laplacian f. Okay, we'll just deal with the last one first because it's easier. Sigma 4 over 4 Laplacian squared phi. And then here we have some weird terms. So we have sigma 2 over 2 Laplacian phi prime f plus sigma 2 over 2 phi prime Laplacian f plus sigma 2 sum of I of phi second phi f prime. And the question you ask yourself is, it's actually really hard already for L2. And the reason is that the reason I can do it fast is that I have some kind of trick that I will explain to you in a minute. But for the moment, do you understand what's happening here? When I say phi prime f, I use Leibniz rule to differentiate. So either the prime f goes on phi, which gives this term, or it goes on f, which gives this term. Yeah? Okay. Then Laplacian phi, the prime f goes on phi is phi. Just I mentioned that Laplacian phi prime f is not the same as Laplacian phi prime f. Yep.
So this is are we in R?
We are in RT.
And what is the prime?
It's a notation that we use a lot in geometry and numerical integration for making things simple. So, you know, when I write phi prime f, what you understand is the Jacobian of phi multiplied by the vector field f.
Oh, so it's gradient.
It's a gradient, yeah. You can also write it as Laplacian phi scalar product with f, right? And phi takes values in R, so it's really a real number. Problem is that after that, I will have to write something like phi second f g. But you can still write the ranges because it's called the Hessian of phi multiplied by g. But I really hate that because we'll have to go with higher derivatives. So we say that phi to the k f1 okay, is simply the sum on I1 I to the dimensional problem of dk phi dx I1 dx ik f1 I1 okay. It's yeah, we don't have to understand this. It's just that that's the real derivative in RT. It's the same as in Lenkian. But let's come back to this. But we have to apply the Laplacian to this differential. So we have first applied to this one, so it's Laplacian squared of phi. Then you have Laplacian of phi prime f. So you know Laplacian is the second derivative. So it has two derivatives, like two edges, and you choose where you want to plug them. So you put the two derivatives on phi, and you get this term. Or you put the two derivatives on f, and you get this term. Or you put one derivative on phi, one derivative on f, or the reverse, which gives the same result, and then you get this weird thing that you don't really know what's happening here. But my point here is that this is complicated. It's really easy to make mistakes because you can't really see what you're doing and what's happening. And if I had to compute L to the 3, then it's a complete mess. So for this, we use trees to present all these terms with their extension.
Can I ask a question about the last term?
Yeah.
Can you just read it? I'm just unsure about what's inside of the parentheses.
Yeah. It's a sum on I from 1 to dimension problem of phi second EI.
Okay, yeah, sure. I'm good with that.
Yeah,
Thank you.
where EI is the ith component of the canonical basis. So I can clearly go to class today. So just stop me if there's something you don't understand. So we'll talk about trees. So these are called virtual trees, and I'm presenting an extension that we can use in this context. So the idea is that when you have complicated derivatives, either you say that their extension exists and you don't work with their extension, but if you have to work with it, you need a tool to trees were introduced by Buncher in the 60s to study numerical integrators for ODEs. It proved very, very useful because we had a moving method of order 5 that was derived from trees, and it had a mistake in the proof, so actually it was not of order 5. The point is that they did the their extension, it was too hard, and with the trees it's straightforward. You can't make a mistake. Then this tree formalism was used by people in analysis. So Kozen-Kreimers won the field medal because of, they did a lot of work, including trees, and they didn't know that they used the same formalism that some random guy in New Zealand invented 10 years ago. Then it was used in geometric numerical integration for a lot of things, but mostly for studying geometric integrators that I will talk about today a little bit. And now it's used a bit everywhere, in rough path as well, by Martin, but also in numerical analysis and other fields, because it allows you to represent and to understand better material expansion. Anyway, so let me present it to you. So we draw some small trees and they correspond to a different one. So if I draw one dot, this is a node, it's the root of the tree, it means the function phi. If I draw another node, it means phi, so the root will always mean phi, and all the other nodes will mean f. This is phi prime f. Now you can guess what is this one. It's phi double prime of f. We can do more like that. Is it okay?
Yeah.
Then you have this one. So this is phi double prime f prime f, and then f on the other side. Yeah? Okay. Now you see that with this formalism, we can take care of all these terms, but all these do not work, because we have an adaptation. So we have to introduce the equivalent of an adaptation, which we will do. This is called a line because it links two nodes, whatever what they are. So this is the adaptation of phi. Actually, if you have okay, let's do this one. You can link two nodes with this line up, and it means that you take the derivative root of the line up. So as we saw, it's by second f prime f. Sorry, yes. Then you take the sum from I equals 1 to b, and you derive both nodes in the direction of the canonical basis at the same time. So it's instead of f, it's f prime ei, and instead of f here, it's f prime. And you see that with this definition here, this is indeed equal to the sum of 5 second ei. Because this is just another way of writing the phi of the dx pi squared, which is exactly the definition. So what we're doing here is that we're taking this dashed edge, we link two nodes, and it means that we differentiate them together in the same direction. Does it make sense? Somehow. Yes? It's just a notation. Anyway, point is we can rewrite L with F. So L phi 1 equals to phi prime f plus sigma 2 equal to Laplacian phi. I will just fix sigma equal to 1. Yeah, we can do that this time. And then we can see that it's just phi prime f plus 1 half Laplacian. Okay. No problem. Now, if I want to compute L25, what I really want to do, okay, I will use query notation. What I want to do is to take this extension and to apply the grafting of a f. Okay, I apply this, but I replace by this. And then we have and you take the line out of this. I just rewrite that, but I replace the node, the group, sorry, by L5. Now, how do we compute that? Well, you take this edge and you link it to all the nodes in every possible direction. So you take this one and what you obtain is this one by linking this one to the root. Then you have this one. And then you have this one. You agree? For a liner, it's much more annoying because you have to take two nodes and to link it. So either you take 2 times this node, or 2 times this one, or this one, this one, or this one, this one.
Do you have to count it twice?
Yeah, indeed. Then what you get is this thing. And this is exactly what we have. So
Yes, of course, now it's so clear.
it's much easier. So 5 second FF is indeed this one, this is 5 prime F from F. And you see that when I say I use Leibniz rule, what I'm just doing is distributing this over each node. That's all. Okay? And this guy here, that's this annoying guy. And
You should drop the same square.
what?
Same square.
Yeah, it's always one. Yes, it's easier. Actually, I hide it in the liner. They prefer to fix it to one. Yeah. You don't need that, but I'm just doing. I think I lose too much time from using it.
Okay, can I ask just
Yeah.
fast now? When you have the Laplacian square of phi,
Yeah.
which one is it? That's that one, right?
Yeah.
Okay.
Because
And the last one is this one that is linked to the you have to. Okay.
it's worth writing within that action square. So this one, yes, it means that you take the sum of I and j, so when b or z or phi x I squared is j squared. Because I also write the I is 4 I j.
Yeah, sure.
But I mean, this is much easier for us. But okay, now you're convinced. You know that it's easier to use this thing, and also if you want to compute L35, and you know how to do it, you take this and you graph it and you treat and you know, and you take the line out and you obtain L35. All right. So that's for the exact solution. Yeah. So what we've done is that expectation of phi of x of h is equal to I of h and s is 1/2 the fraction plus h squared over 2. I will just say squared, but this is just writing it somewhere because I won't need it later. Yes, 24. Yes, 1. So if you're wondering, it's because I had h2 over 2, so I had to multiply everything by that.
Yeah, it should be a fourth on the third term as well, maybe.
No, because it appears twice. I'm super fast with these calculations, I'm sorry.
That's good.
I've done them too many times. So anyway. Now what we need is expectation of y of x1 as a numerical solution. All right. But which integrators do we want to take? It's not clear that any integrator would satisfy such an extension. And in practice, it's not the case. So I will give you a class of methods that do it. It may not be the best one, as we'll see for manifolds, but wow, okay, it goes fast. But we will see how it works. So for ODE, we have what are called fungible integrators. So basically, you take some intermediate substages that satisfy something like x plus. This is the initial condition, by the way. H sum of aij and you have S substages, and then you have y1 x plus h sum of bi f of y. So for instance, if you take aij equals 0 and s is equal to 1 and bi is equal to b1 is equal to 1, so so we find y1 is equal to x plus h f of x. And this is called the Euler method. For SDEs, we do the same. We have yes f of x plus sigma e to the u. Again, this is just additive noise. I will talk a bit about the multiplicative noise later. And what we do is we say yi is equal to x plus h sum of aij f of yj plus sigma equation di side, where this is additive for equation law. And it does the same for the left side. Okay, I have fixed sigma is equal to 1 and so on. You can add some more noise, you're free to do whatever you want, but we'll just do it. So the idea is that you build some approximation of f of x by taking some intermediate points, and you just replace dw by a random variable that has the same flow. An example right now is the following. We saw in particular the Euler method for SDE. So, for instance, you have y1 equal to x plus h f of x plus, wait, I knew it. Alright. First part of h. This is what we call the Euler method. Last week. So just note that I just replaced in this, I replace f of x dt by f of x h, and dw by square root of h times by a random variable that has the same load, and that's all. That's an example. This is the order. Now, truth is, you can prove that this class of methods has an expansion in trees. So, what we want to compute identify my sorry, use capital methods in the stochastic framework. So we want to compute expectation of y of x1 and show, as here, that it satisfies an expansion in trees. All right? So what do? Is that we actually compute it. Y of x1, we have yi is equal to, okay, I won't go fast because you don't need to know how to do this. So h the other side. You take that. You say that yi is equal to x plus equal plus square root of h the other side plus h sum of aij f of x. That's all. I just put the terms in order and I replaced yj by x. Because I said that yj is equal to x plus something in h. Now I take that and I put it in here. So x1 is equal to x plus h, okay, plus square root of h, right? Plus h sum of bi f of yi plus nothing, okay. And I will replace f of yi by a direct expansion of f of yi around x. Believe me. Just believe me. So what you say is something like that, bi f of x. If I don't write the x, it means that it's f of x, because I want to get it in the future. And then you have plus h cos of h sum of bi f prime side plus h2 sum of bi aij f prime f plus sum plus 1/2 sum of bi squared f second prime. I'm good. Or completely lost. I'm just doing theory expansions as normal in RD. Just believe me, it's the result.
Yeah, I'm already putting quite a bit of trust in.
It's just annoying applications. I'm doing it for you.
Thank you.
Okay, so what's the difference between y and x? The capital Y, capital X?
It's like y plus some. Okay, the idea is that you have your method like this. So this is the exact solution.
Yeah.
You have x. And the other method tells you to take the slope here and
Take one step in that direction.
you take one step, blah blah blah, and you end up here.
Yeah.
But
So you've got y1 and not x1?
so y1 is because it's deterministic, which is equal x1. It's just a confusing choice. A confusing choice of notations.
Okay.
Oh my god, I'm so scared. Anyway, so let's write x1. And the yi is that instead you take some point, for instance, in the middle, y1, and instead of doing one step like this, you will do a step like this, but with a mix of the slope here and the slope there.
Yeah.
for instance, if you take an average of the slopes,
Uh-huh.
ends up here, which is closer.
Yeah.
And that's called the doing method. I think it's, I don't know. Anyway, you can think like that. That's the idea. You take some point in the middle and or not in the middle, and you find some intermediate slopes. Yeah.
Could you do this, like, do you need to have two characters X and Y? Could you write it all out in one?
So yes, you could,
Uh-huh.
if this is explicit. So you see here,
Yeah.
if ai is different from 0, yi is also here,
Yes.
so it's implicit. So you cannot write it
Okay, I see.
and then you will have to apply a Newton method. So blah, 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 and I won't talk about it. Yes.
So maybe this is the one question. Even deterministically, Euler's method, Newton's method, et cetera, can have convergence issues.
Yeah.
Is there some sort of guaranteed convergence, or probability, probability, something like this?
This is actually kind of a good question, because it's something that most people think. If you don't know numerical analysis, you don't understand why we have so much to do, because this should just be a perfect integrator. But the thing you learn is that it does not exist. If you want an integrator that is very, very accurate, it will typically be very unstable and very costly. If you want a very costless method, it's everywhere. If you want a stable method, it's not that great. So, no, clearly I forgot on stability. If f is crazy, this is completely crazy.
And let's say if you have that as analytic or something, and you don't trust that.
I say here that f is very regular and does not contain crazy relations. It's not 1000 somewhere. And also you see that I always write plus dot dot dot, but what is this dot dot dot?
But it's in one variation is very small, relatively small, like this.
Maybe not very, yeah, in a way, yes.
There's some
There's a three modes of derivatives of that. I will just finish and then we take a break. Okay, sure. So just admit that I know how to do this. You can do this. It's just a theory extension. Believe me. Then you believe me that you have phi of x1. I do the extension of phi of x1 around x. I just take everything. And again, I do the extension. So we get something like phi of x plus phi prime psi plus h sum of phi prime x plus when we have phi second psi plus h versus of x something blah 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 blah. Yeah. And then what I wanted to compute is this one. So I have to take the expectation of it. I take the expectation of it. This is assumed deterministic. This is expectation of psi is 0. We did the calculation 2 weeks ago. Because it's a Gaussian law, it's centered, so the expectation of psi is always 0. It disappears. And it turns out that the expectation, this is deterministic, no problem. And the expectation of this is, let's do it. This is the expectation of sum of I of d by dx j. Expectation of psi I psi j. And we've used that a lot in the course already, but the expectation of the product of independent Gaussians is 0, because then if I is different from j, you can just do this. This is another expectation here, and it's 0. Okay? But if I is equal to j, first I can just do this. It's xi I squared, and this is the variance of xi I, which is 1. So what I get is the Laplacian. Laplacian appears. It's not magic, but the thing is, in the end, if we forget all this technical that is, I'm sorry, I'm very sorry. But in the end, what you find is the following: at expectation of phi of x1 equal to phi of x plus something, and actually you can see that wait, phi prime f is actually this 3. The Laplacian of phi is actually this 3. So I can rewrite everything with truth. And I will do it. So I need to keep
So the idea now becomes that the sum of BI must be equal to 1, so on.
yeah, exactly.
Okay.
Exactly. You go too fast. So plus HQ, and here it is. Oh no. Oh no, that's not the green one. Just bear with me a second. And yes, it is. Sorry for this awkward silence. This is actually fun. But the point here is that a machine could do this, while a machine could not work with differentials. It's very hard. It's so annoying. But the work with trees is much easier. So a machine can definitely do these calculations for us, which is fantastic. We don't want to do it ourselves. Right. So after this tedious calculation, on this, and you see that if sum of BI is equal to 1, you have a method of order 1. If sum of Aij is equal to 1/2, if sum of BI is equal to 1, and this is equal to blah blah blah, etc., you have order 2, and you can do it for any order. So we'll just write this here, right? So what we do in practice, to make a table, you have the order 1 and 2. You have a tree and a condition. And what's amazing is that to each tree, if there's a tree here, there's one condition. What I mean is that the conditions are not redundant. You will not have the same condition for 2 different trees. It's one tree, one condition. So here we have sum of Aij, blah. This one we already have it, it's sum of BI is equal to 1.
So it's kind of redundant.
Okay, yes, but no, because
This is a square.
okay, this usually you assume it always.
Yeah.
A this is not really a condition of order one.
No.
Because you consider only consistent non-computer level. So I understand your point, but in fact it's okay. Like this is an okay redundancy. So anyway, so the is squared is equal to 1.5, and so bi is equal to 1.5. And you see that you have one condition for order 1, 3 for order 2, then you would have 9 for order 3, and it grows exponentially. But at least there's a way to do all this instantly with the computer. Actually, this Taylor expansion that I made here, you don't have to do it. You can derive the coefficients immediately with some algebra, but I didn't want to do it. My point here is that this is already much harder in the deterministic case. In the deterministic case, you don't have the lioness, you have one condition for the two, this one, and then you can just find the deterministic conditions in this table. But the problem here is that I considered the equation the following. I promise I will take it right. The equation we consider here is the following. But what is really interesting for people is to have a function. Turns out that it's really hard. If you want to make the Numerical method for this, you cannot just take the same Numerical method that I gave you before and say, well, I just write j of y j times 5. If you use only quotients, it doesn't work for some reason. If you use multiple quotients, it also doesn't work. And the only reference in the literature that exists is with T2 nodes. So we actually use some psi, some xi squared, and manage to reach order 2 at the price of 59 of the conditions. And it has been reduced by some Chinese people, if I remember correctly, but it's still completely crazy. This is just an order 2 method. There's only one condition for all these, and 3 here. And this is still not a question to know if there's a good set of Numerical integrators that would have less conditions, especially non-redundant ones, because they are of course redundant, and with a tree formalism that goes with it. It's always hard to have a problem and find at the same time the tree formalism for studying it and the set of methods that go inside, because you want the tree formalism to be the smallest one to study this class of integrators. And I mean, in geometry numerical integration, we're very interested in finding the right set of methods, especially for problems like that. That is work to be done. And we'll take a break. And then we go on methods. Is it okay? I went a bit fast. Did the recording make sense? Okay. So I said a lot about how it works in RD. I admitted a lot, I'm sorry about that. But now we can just talk a little bit about how it works in the minute. So I will explain what changes and what is yet to do. So I take a manifold M embedded in RD, a set of points in RD that satisfies a set of conditions given by a function zeta, right? Zeta can be of size. I mean, it can take values in RQ, then you have a manifold of codimension Q. But nothing is done for codimension Q, so we'll just take zeta from RD to R. So there's a few schemes of order 1. If you work in higher codimension, but we'll just take R. So so it's the sphere. The notional equation is slightly different. I gave the example before in the course for that means you do that. You have the projection, like the complex, and we will again take additive noise, but it's not additive anymore because you have to project it. So what you do is you project on the tangent bundle at every step in a way. So by n here, we define g of x is Laplace beta. The ground matrix, which is just a real number, is equals to g. And pi is the orthogonal projection in the tangent bundle. This is the identity matrix minus the c minus 1 of x, g of x, g transpose of x. It's just, you can recognize an orthogonal projection here. My point is that you have a manifold, and you have the exact solution that starts with x, and goes on the manifold, blah, blah, blah. And of course, you have numerical algorithm that starts here, that takes that ends completely out of the manifold, and what we obtained that the previous theory that I did in the previous hour is useless because we have to stay on the manifold. Right? So what we did before doesn't work. And we have, even if we discretize this thing, it's almost sure that the new step will not lie on the manifold. So we have to be clever about this. So before talking about numerical methods, I will just present again how to do this. So you remember that we had the exact solution. We had the definition of phi of x of h. It's the same. It's phi of x plus h and phi plus h and phi. Blah blah blah. But n is different now. N is actually given by the following. Here comes the fun. And problem, the tree formalism that we used before, even if we extend it, it's not straightforward that it works with this. So I've tried a few formalisms of trees. Turns out that at some point, there are some derivatives that I cannot represent with this formalism of tree. This is an open question. If you have some ideas, I'm very interested.
Like you mean that there is not a contradiction, but there is something.
Like you need some different trees. And what you would like to say is to say, okay, this is phi prime phi f. Okay, instead of f, it's phi f. Then you want to say it's 1/2 times phi second. And this is phi m ei. So let's say that it's phi m and phi m, and I link them. This is a good guess. Then you have 1/2 phi prime phi pi, and this seems to work, but it does not. Like you miss a few. Yeah.
What exactly is meant by pi?
The orthogonal projection of the tangent bundle at point x.
Orthogonal under the standard calculus. I mean, almost certainly, yes.
Yes, sure, yeah. Anyway, I tried. It doesn't really work. So of course we replace it by the Euclidean derivatives that we hate so much. But for the moment it works. And if you are able to help me with this, I am very interested. Anyway, what we obtain with GPD and derivatives is the following. They have to write this once. So you see that you have some new terms. Plenty of derivatives, but you have new terms that are completely different with divergence and stuff else. Like there's a divergence here. Scalar product there and there. Still an adaptation, still a normal derivative, and 5-second GT. So for the moment, we'll forget that G exists, so we'll fix it equal to 1. It doesn't matter anyway.
What is capital G?
It's
Oh, yes.
the norm squared of the derivative of the gram matrix. But it's not a matrix. What's that? I will be ready for that. So anyway, you can extend the formalism of trees to take this into account. And what you find is L5 is equal to 5 prime f, the same as before. Then you use G, it's an empty node, a white node. And if you link it like this, it's a scalar product. Okay, so G is scalar f 5 prime G minus 1/2 divergence of G. And then you see how wide it is becoming. But it is actually some minimal formalism to write all the Euclidean derivatives. Blah, 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 just going to have that question. This is for order 1. If you want to compute L2 to 5, this expression takes 7 pages. In this form. Yeah. In this form, if you try to do it by hand, kill yourself already. Yeah.
So you have an algorithm or a computer that generates it.
No, this I actually do it by hand.
But it's, I mean, it's completely.
It can be done. Yeah. So about the computer thing, like even in the RD case, we observe some crazy things. I don't say this too loudly because it works fantastically. But there are some things where you know, for instance, that n star is equal to 0. It's a design condition. And we know how to compute this even with a computer. But so you can understand that this square is also 0. This is also 0. But with a computer, this is not 0. And you need the help of the human to say, oh, here, if it wants simplification too much, you have to go back and put a coefficient, and then you would obtain 0. So I would say that everything can be done with a computer to a certain extent. Like some algorithms, it's not clear that they finish with the help.
Is it compare the algorithm or is it
I
compare?
don't know, this is just that the problem is actually harder than we think. But this is something that I won't talk about today. But this is like, even with a computer, it's hard. But anyway, we have this. So we can compute an extension like that with an extension that is crazy old. But now I want to talk about the numerical solution. There's only a few methods that exist in the literature. And the one that exists are projection methods. So, for instance, the projected Euler method is given by the following. You take a step of the Euler method. As before, the same one. And then you realize, oh, I'm not in the middle. So I want to build a manifold. This is a set of constraints. If this is 0, it's done. And then you realize, but this will never be a manifold. So I add an add-on multiplier, and I fix lambda such that this is 0. So what we really doing here is that you take a step out of the manifold, you take the normal to the manifold here. So this is g of x, and you project it back, which works if you stay in the neighborhood of the manifold. But if you don't, if h is too big, it's a disaster. And
You mean it's a disaster because you take G that doesn't really project out.
but I mean, for the sphere, it's clear that you should take the direction of the manifold here, the one that's really tangent orthogonal here. But for any other manifold, it's the same. It's equivalent. So really, there's no proper direction to take here. So this is the only method that is used by everyone in engineering, and yeah, everyone. I'm sorry. And nothing, and well, I will tell you a bit more about how it can be generalized, but it's just crazy, all those stuff that we have. I'm not talking about the Lie group methods for stochastic problems because it does not exist. I mean, I couldn't find anything for this kind of problems. I tried to type stochastic Lie group methods on Google and on Google Scholar, and nothing came out.
This specific thing you're talking about should be relatively straightforward, unless I'm missing something on the group.
Yeah, on the Lie group, yes, but I can't find much.
I don't remember think about it, but we group there's a solution to the problem.
And I would like to see references. Really, like, it's actually useful. Anyway, if you want to generalize cases of Runge-Hupyter method, it turns out that the first case that you can take is the following. So you take f plus h from Pij f of 110 plus so the same as before, di, right? But then it turns out that it's not enough if you just take plus lambda g of x. You can never reach all the 2's. What you have to do is to take lambda sum of ai and impact and g of y. So instead of projecting in one direction, you take an average, a complex combination of the projection directions. Then you can choose that or not. And we will always project here for simplicity. And then you take the same thing for x1. 1 is x plus x of p1 first of h side and so p at g proper. And here's where it works. Turns out that you can do the tree formalism works here. It's crazy hard. It's just redundant. There are 7 pages, more than 12 pages of trees to express that for all the two. It's not straightforward at all. And it only works with the dimension 1.
Can I ask a question here?
Yeah.
Because the problem here is that you're working on embedded manifolds and
I use Euclidean here.
yes.
Yeah.
I mean, shouldn't there be an easier way to solve this using exponential maps and geodesic flows and so on?
Well, maybe.
This is one of, I think, 3 different ways I think you can approach it. Yeah, this I think that's what I was thinking. This solves exactly this problem.
I want to see. So anyway, here's the kind of instrument that you find. This is just crazy pages and pages of these. I just need to find the number of conditions. What time is it again?
35.
35?
Yeah.
Fantastic. Anyway, for order 2, for this set of methods, if I project every substage, you have 3 conditions for consistency, that is only 1 instead of 1, and yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 conditions for order 2, which are pretty redundant and come after 12 pages of calculation. So I would say that it's good already because this is the first thing. I mean, this is already better than nothing. But it turns out that this set of methods is probably not the good way of tackling this problem, clearly. Especially because it comes from the nature of this kind of methods that we do not. I think that just taking these methods implies that we'll get some redundancies and that we cannot write a solution in terms of the trees I presented earlier. Because as long as we can find a class of methods that can be written with simple trees that use intrinsic derivatives of the manifold, then everything becomes immediately easier. But again, I just wanted to tell you what exists. Right. I would like to present just an example in a very simple case. Here it is. An example that is useful for everyone is equal to dx equal to pi n x. This is the drawing motion on the manifold. The question is, how can I make a method that is not just a folder one for simulating a drawing motion on the manifold?
I know you answered this already, but one more time, exactly what is this pi m?
Pi m is yeah, I can do it. So we have x and pi m is this is a tangent bundle on x, whatever. I don't have a notation, whatever. Yeah. And basically project orthogonally on this is y, this is pi m pi m x.
Maybe I can ask a quick clarification. So you have the codimensional manifold in RV,
Right, it's yeah, whatever, yeah, sure.
so the thought that you have codimension one manifold in RV,
Which is simplification, but sure, yes.
or just arbitrary manifold.
Arbitrary would be
Arbitrary manifold in RV, you pick some point on the manifold, either x0.
Yeah.
You run just a regular rounding motion, dx equals x, showing which dw.
which goes up to the manifold.
Yeah, and then project on the manifold.
Okay. So this would give a first order approximation of this.
Okay, so then what's different with this? So this is somehow you're projecting a tangent space?
No, it's a solution. This is one definition of the polynomial manifold. It's just that you can understand it as I make a step and I immediately project it on the manifold.
The manifold, the tangent.
Yeah, so yes, it's on the tangent space, but as you do it with an infinitesimal time step, you stay on the manifold. But of course, you can't do that for numerical scheme because you don't have an infinitesimal time step, whatever. Anyway, if I take my manifold to be as here, then it's so easy because the solution is just x of t. It's just exponential of some line motion and so.
The exact solution.
Okay, s y Yeah, okay, so.
How about we just draw it in S1? If you draw a circle, you try to see what.
Yeah, I just get the one t plus 5.
What is this?
I just going
These are the two components of a two-dimensional, right?
Yeah, well, that's what I made exponential, but whatever. Anyway, so it's so easy. If it's a Lie group, you have the exponential. It's very easy to get an exact expression of any Brownian motion on the manifold. If you have a general manifold, it doesn't work. So what you have to do is, again, what exists is to use these projection methods. And I plan to use the only method of longitude for solving this problem.
I kind of still don't understand what this pi m is.
Okay.
It's very difficult. Okay. I'm sorry.
No, it's
Can you maybe draw it visually? So you've got the sphere here. So take a point on the sphere and.
wait, I can just say, so you have a vector n that is orthogonal to the manifold
Okay.
in the dimension one.
Yeah.
So basically what I'm saying is that phi of x is identity minus okay, y is another vector general quantity. It's v n, and n is normalized. That's what phi n is. It's just, it takes out the component that is orthogonal.
Yes, you say that you have a way to project RD down to the manifold that is codimensional in RD.
Not the manifold, but the tangent space at this point.
You're imagining the tangent space embedded in RT.
Okay, yeah.
So in the case of a sphere,
Yeah.
two-dimensional sphere, it's you take the starting point, you imagine the plane tangent to the sphere. You run the motion in R3 and then just project on the front.
Okay, yeah, sure, then I'm good, I'm good.
Sorry, I don't know perfectly differential geometry. Maybe I don't think the things right.
So you project onto the tangent plane, tangent space at X.
Yeah, yes.
And
Okay,
you
yeah, yeah.
exponential at 0, x0.
Okay, sure.
An example method just for this simple case is the following. Like xn plus 1 is xn, which will put h side plus lambda multiplied by 3xn over h side n plus xn plus 1 divided by 4 and theta is 0. It's not obvious, right? It comes out of nowhere. And yeah, it comes out of nowhere. And that's the simplest we found. Notice that it's implicit in xn plus 1. It's implicit in lambda because you actually have to find lambda such that this is true. This is heavily implicit. In practice, if h is too big, this will fail dramatically. So if you don't take a compact manifold, for instance, you have to take h with respect to where you are. So h should be, you should not be able to make a step that is too far from the manifold, which is especially annoying when this is random and can be as big as you want. So there's a trick where you can replace this with something that is bounded, but still it's very interesting because this is not really what you want. So voila, this is the state of the art. I mean, no, that's not how you say it. That's yes, what exists.
Absolutely.
Okay, this is the state of the art in this field. It's not perfect. There's a lot of job to be done, so you're welcome to help. But the main problem is that you have very tedious calculations to do. Tedious that, I mean, a computer can help, but it's usually not enough. And we have some questions about things. It's not clear if the formalisms are well defined, if we pick this good set of methods or everything. So there's a lot of questions and a lot of work to do. And just to finish, so of course, everything here is in the dimension 1. With additive noise, the question of multiplicative noise on manifold is just so far from being treated that no one dares to focus on it. And yeah, another question, as you said, is that it would be interesting to rewrite everything directly on the manifold, not on a manifold that's embedded in on it. And just I have
Good job.
I have a time. So all of this would be especially interesting if you consider the inbound measures. So I've talked about weak approximation, which is already enough. Another thing that I said is the inbound measures. So it's approximation of the temperature of the system at equilibrium or anything at equilibrium. And this, instead of, so you have a expectation, okay, is not okay. I don't want to go into details, I just want to show you the toys that we play with and how do we play with them. So you have expectation of time of x. Okay, 5 plus x plus 5 plus h2 is 5, that's 454. And then you have the same thing for the numerical approximation. So it's something like 5 plus a1 a05 plus a15 and whatever. And you have a way to have access to them. Turns out that in this context, the order conditions are given by the following as AI5, AI star multiplied by its inbound measure as a non-topology is 0. So what you want to compute is not to compare these two terms and say that they're equal. You want to compute the adjoint of something, especially in the numerical case, and prove it 0 under some conditions. And to do this, for instance, I won't go too far, but you have a process. For instance, in the simplest case that we've seen before, we have this. N5 was given by this family of trees. And if you want to compute the adjoint, for example, if you want to compute the adjoint of this tree, we just unplug the liner, plug it to all the other possible nodes, that is none, and then you plug it to a new node with a minus, and you will get this one. And so this will be equal to 0. If you take the adjoint root by 0. And whatever, there's a process to do this. It's especially tedious in the manifold case. That's why you get 12 pages of calculations. But my point is what I was saying before. We know that L, K, star is always 0. So for L star, for instance, we had something like that. That's not the term. And we typically begin with the term to the most finest. So you would say that this is something like this times -2. Then you put it inside, you simplify, and you go again and again and again. And the computer can do that. And then at the end, you find 0 blockages because it's mathematically proven that it will be 0. Turns out that the computer fails this one. And it's even worse because in the code, it was my student Eugène who did that, and he came up to us saying it doesn't work. And of course, I did not believe him. He came actually with an example with case equal to 4, where his code, he had many choices to make. So he just picked a tree, picked a lion, so it was a tree like that. So he had to pick a line up. So the algorithm was picking this one or this one randomly, thinking that at the end it would amount to the same. And so half of the time the algorithm would yield 0, and half of the time the algorithm would yield something completely crazy. And during something that we thought would finish in some ways with the same is actually not commutative. And for n to the 5, a human is not enough to correct the code itself. Like, we know that it's 0, but it's not 0. And it's especially important because for this, we know that we should find 0. But for this, we don't know what we should find. So it's a big deal, we cannot simplify it. Yeah.
What I'm surprised by, and maybe your explanation will get it, but it seems like this is a deterministic process.
It is.
Then it's hard for me to understand how a deterministic process with
Ah,
a fixed set of rules.
It's because of the way he implemented it.
Okay, so this is a programming problem.
It's a program. Because he said, well, this will give the same result whether I begin with this one or with this one. So when he just picked one randomly, but it doesn't.
So when you say the algorithm picks one randomly, it was more like student programming algorithm.
Yeah.
Okay.
But it makes sense. I mean, I would have done the same. I even almost wrote in my papers that, yeah, I mean, I wrote that this process finishes all the time. It's deterministic, but I didn't plan that it would actually not be sufficient. That you have to make choices along the way.
So because of the nature of the problem, it is clear now that we are aware of how to make this choice correctly.
No, because sometimes, especially for order 5 and after that, you have to say, well, take this tree, decompose it in 2 with coefficient a1 and 1 minus a, or a and 1 minus a, and for the coefficient a, you simplify this one, and for 1 minus a, you simplify this one.
There has to be a deterministic algorithm that can correctly make this choice.
Yes.
It's not clear what it is, what the algorithm is.
It has to exist, but the fact that it should give 0 here means that there's a way of doing the integration by parts such that you could find 0.
It's just not known.
It's just not clear.
If a human does this, is there a problem? When a human actually carries this out, is it, do we get it correct?
Oh yeah, without the trees, no one can.
Without the tree, I mean with the trees.
With the trees,
So,
there's still a problem. It's not here.
so if I understand correctly, it should be possible to rewrite it so you see that's equal to 0, but it's also possible to rewrite it so it just looks worse, but it's still equal to 0, right?
It's not equal to 0, but you have to unsimplify it, to go backward in the algorithm and do it in another way.
Exactly right. So it's just that you don't have found a correct way of rewriting it to end up at 0, because you might start rewriting it into something that just looks worse.
Yeah.
Okay, that makes sense.
But I mean, the thing is that you count the number of lioness that are linked to the root, and you unplug them and plug them somewhere else. So the number of lioness linked to the root always decreases until it reaches 1, and then the algorithm stops. And then you're supposed to find 0.
But it might be that the algorithm was able to rewrite it to something that had that wasn't the proper form where the algorithm stops rewriting, but just written out as something ridiculous and not 0.
And that's happened. That's what happens.
Maybe you're generating equations saying that this whatever ended up with is also equal to 0.
Maybe. But the solution for us humans is to just, whenever we have a choice, we put the coefficients and then for this one we simplify this one, for this one we simplify this one, and then we go on, and at the end we find the coefficients such that everything is 0. I mean, this is crazy.
Real coefficient or?
Oh yeah, real coefficients.
So you say that this is true no matter what you choose for A.
Like I'm just saying that. Yeah, I'm going a bit far here, but I'm just saying that it's not clear which choice we should do between the lioness to simplify, and so you have to pick one, but maybe it's a combination of the two at the end.
Yeah, so you just say that A times the one choice plus 1 minus A times the other choice is equal to, like, it's equal no matter what you choose for A.
Yeah,
Yeah, okay, so, okay.
and then at the very end, we try to find A such that it's the solution we want. Whatever. I think I will stop here. There's a lot more I wanted to say, but I think it's better if I stop here. The idea that I wanted to give you is that there's a lot of applications, not only in finance or anything, but also in molecular dynamics, especially. And people are really craving some efficient methods. And well, the ones that I presented are actually quite decent because order 2 is already very high order for SDEs because it's hard to obtain, but also, as I said at the previous course, because you have Monte Carlo error and other types of errors along the way. So all of this should be combined with other methods to reduce bias integrator, to reduce Monte Carlo estimate, whatever, everything. But the point, and the most important thing here, is that the theory that we have for obtaining a high order, to my opinion, it's not finished. There's a lot to be done. It works in RT, the very simple case, but then as soon as you take some multiplicative noise, or you take manifold of higher dimension, this just gets crazy and it goes for help from geometrical version versus story. And I think we'll stop here.